Hello, good morning everyone. Here in the next example, as we have discussed in the last class, we will take another example where the transfer function will be something different from that of the previous one. And you see here the transfer function is written like this. And here why I am just solving this problem, and parallelly I will draw the graph like this structure. So first of all, what you have to find out, first of all, number of open loop poles, that is number of open loop pole. I just write this for the next time. Open loop pole, what are the number of open loop poles? You see there is a third order system, so this will be 3 open loop poles, and within bracket what to write the pole positions. You see here you will do s into s square plus 2s plus 2 equal to 0. From there you get s is equal to 0 and s is equal to minus 2 plus minus root over 2 square minus 8 by 2. That is, we see minus 1 plus minus j1, right? So there are 3 poles. One it as s is equal to 0, this is real value, and minus 1 plus j1. So minus 1 plus j1, minus 1 minus j1. These are the 2 poles. So minus 1 minus j1. This is the pole. So m, here also there is no open loop 0 exists, so m is equal to 0 exists. Next step, how many number of branches will be there? Number of branches will be equal to the number of poles. So number of branches will be 3, right? And next step, what are the number of branches terminating at infinity? So number of branches terminating at infinity equal to number of pole minus number of 0. That means you see n minus n number of branches terminates at infinity, because there is no 0. So 3 minus 0, so 3 branches terminates at infinity. When we will call these 3 branches will terminate at infinity, that means they will go differently along the asymptotic path. So next step, we have to find out the asymptotic angle. So phi is equal to 2q plus 1 into 180 degree by n minus m, where q varies from 0, 1 up to n minus m minus 1. Okay, so what is this value here? In this case, this is also 2. So once this is 2, so we will have to find out the value of q from 0, 1 and 2. So we will be having 3 values. So for this particular problem, this phi a will be having 2q plus 1 into 180 degree by 3, where q varies from 0, 1 and 2. So if q varies from 0, 1 and 2, we get 3 angles, that is phi a1, that is 60 degree, phi a2, 180 degree, and phi a3, that is 300 degree, right? So 3 asymptotes we will get. Next step, once we get the asymptotes, next step is to find out the the meeting point of the asymptote on the real axis, that is known as centroid. Okay, that is centroid is defined as, that is summation real part of poles minus summation real part of zeros, right? So here the summation real part means the poles we have to consider 0, we have to consider minus 1, and we have to consider minus 1, because only real part we have to consider, right? So this is 0, minus 1, minus 1, summation of all the real part of the poles minus 0. Okay, by n minus m by 3. So minus 2 by 3 minus 0.6x. So this is the centroid. So the calculations is almost over, right? You have calculated the number of open loop poles, you have calculated the positions of the open loop poles, you have calculated the number of open loop 0. So once you calculate the number of open loop poles, that means there will be as much as number of poles, the same number of branches. Number of open loop, the branches will be 3. Once there will be 3 branches, so they will try to terminate either 0 or infinity. So is there any 0? No. So all the branches will terminate at infinity. That means 3 branches will originate from open loop pole, and they will also terminate at open loop 0. Now once they will open infinity. So once they will try to go to infinity, so there is a path. That path is known as asymptote. So asymptote means there will be certain asymptotic angles. So asymptotic angles is given by this formula, where you get n minus m minus 1, that means 2. So 0, 1, 2, these three value of q will give you three sets of asymptotic angle: phi 1 60 degree, phi 2 180 degree, phi 3 300 degree. Once you get these three angles, so how these angles will be put on the real axis and how these asymptotes will meet, so that point is known as centroid. So centroid means summation real part of the poles minus summation real part of the zeros by n minus n, and we have to consider only the real part. So 0 is the real part, and minus 1 plus j1, out of this real part is minus 1, minus 1 minus j1, real part is minus 1, so we get minus 0.66. So these are the calculations we made. Now we have to take 1 millimeter graph, and on this graph we have to place all these things we have calculated here, right? See, this is your millimeter graph, and I have just pointed or scaled these values. This is 0 to minus 1, so this is 0 to 1, this is 0 to minus 1, and this is plus 1, and this. So what are the pole locations? We see this is s is equal to 0. There is a pole at s is equal to 0, right? But this is open loop pole, means gain is k is equal to 0. This must have to be right, because without this signifies nothing. So at s is equal to 0, the value of gain is equal to 0. Another two poles at minus 1 plus j1, s minus 1 minus j1, that means they are complex conjugate to each other. So how to place this? Minus 1 real value and plus j1. So this is the open loop pole on the s plane. So here again the value of k is equal to 0. The pole may be in the real axis, maybe imaginary axis, whatever, wherever the pole is placed on this s plane, the value of k at that position is equal to 0. And another pole is minus 1 minus j1. So this is the minus 1, and you see these positions is your minus j1, where again the value of k is equal to 0, right? Now the thing is that we have calculated the value of centroid. What is the value of centroid? Centroid was 0.66. So 0.66 is the point we have to identify on this real axis. So maybe this is centroid. S is equal to minus 0.66, which is centroid. And where you have to put the protector and make all the angles anti-clockwise. Again I am saying that all the angles are to be measured in anti-clockwise directions, right? So 60 degree angle, we have to draw one 60 degree angle. Say this is your 60 degree, this is 180 degree line, this is 60 degree line, and there is a 300 degree line. So three asymptotes I have drawn with the centroid. Next one was the point, the root locus branch is symmetrical about the real axis. That is the last point we will find out. And next is that there is a point. See, the point was you have to find the branches on the real axis. Branches on the real axis, that is very much important. So identifications, the branch on the real axis. So how to identify this? You have to consider the rightmost pole and see whether any pole to the right of this side. So there is no pole. So you have to consider any point to the left hand side of that particular pole. So you may consider this point here, you may consider this point here, you may consider the point here for this case, because there is no pole or zero except this. So this point means same, this point means same, and any point on the infinity is having the same features. So we are considering this point here, and we have to consider the total number of poles and zeros at the right hand side of this pole. So total number of pole plus 0 at right hand side of that point is odd or not. So here you see at the right hand side of this, what is the total number of pole plus 0? 1, that is odd. So there is a branch which starts from here and ends up to infinity, because there is no pole or 0. If there is any pole or 0, so after that pole or 0 there may be one branch. So we may just highlight that branch with red color here again. So this means there is a branch, right? So that part is over. Now what is the next step? Next step is to find out how to do and what to do. K is equal to 0. Now use your common sense. 3 branch, one will start from here, one will start from here, one will start from here. 3 will go to infinity. One will go along this asymptote, one will go along this asymptote, one will go along this asymptote, right? So next you have to find out, is there any branch available through which the poles can go to infinity? Yes, there is a branch available. This pole may goes to infinity along this path because there is a branch and also an asymptote, 180 degree asymptote. So this pole and this branch, that means this pole will terminate at infinity when the value of k will be infinity. So one branch is complete. Now we have to find out the next step, that how this pole will move to infinity along the asymptote. There are two asymptotes left, one is this, one is this, two poles left, and next step was to find out the breakaway point, right? Breakaway point. So first of all you have to judge from the given figure or drawn figure that whether the breakaway point determination is required or not. See here, is there any two poles staying side by side on the real axis? No, there is only one pole is on the real axis. So how can it be possible? So no two poles are residing side by side and there is no branch between them definitely. So breakaway point determination is not required for this problem. So there will be no breakaway point, right? Next thing is that, is it the branch which will originate from this open loop pole and this open loop pole will terminate at infinity along this asymptote and this asymptote, and will this cross this imaginary axis? Yes, that is the point, and we have to find out, if possible, the point of intersection with the imaginary axis, right? So breakaway point is not required. So next step is to find out the intersection point. Intersection with imaginary axis. So how can it be done? With the help of Rout simple. So 1 plus GSHS equal to 0. This will give you, like, you can say it in the sense that this will give you 1 plus ky s cube plus 2s square plus 2s equal to 0. That means s cube plus 2s square plus 2s plus k will be equal to 0, right? And if this is the case, then by using the Rout array we have to find out the value of intersection point. So we will consider the Rout array in this case and see. So Rout array, this is s cube s square s to the power 1 s to the power 0, and you say what are the values. This is 1 to 2k, this is 4 minus k by 2 0, this is k, right? So this has to be 0 because this is 0. Again I say this is 4 minus k by 2 equal to 0 gives k is equal to 4. That means gain where this will actually intersect the imaginary axis is k is equal to 4, and the point of intersection will be calculated based on this point. That means this is 2s square plus 4 equal to 0. That means s square is equal to minus 2, s is equal to plus minus j root 2. So we find the value. That means here actually the branch will originate from here, will terminate at infinity along the asymptote, and that will definitely intersect the imaginary axis at j 1.414, like this point. So this is your point plus j root 2, this is your say minus j root 2. So you will have to pass through it and along this line. So we may say this is your termination point. I mean, from the concept, you can automatically say. Now the thing is that how the branch will originate from this open loop pole, because this is a complex pole. So that is the difference between the previous problem and this problem. Here the previous problem was that in the previous problem there was the poles which were located on the real axis. So if the point was located on the real axis, you say what happens. In case of real axis poles, the root locus branch originates or leaves the real axis at an angle of 90 degree. But here in case of complex pole, that is not going to happen. So what happens? For complex pole, that term is known as angle of departure. Okay, so we will calculate the angle of departure for complex pole, and is these two poles are complex conjugate to each other. So if one angle of departure phi d is calculated, so based on that this will be automatically calculated. That means if this is positive angle of departure, this will be minus angle of departure, and with that concept that the root locus branch is symmetrical about the real axis, we will find how to get the you see the root locus plot. Okay, so now we are going to get the angle of departure calculation for this particular case. So how the angle of departure will be calculated, right? See, for that, first of all, connect all the poles and zeros with pole under consideration. That means what? We want to find out the angle of departure for this pole. That means what you have to do? You have to connect with this pole with all other poles on zeros. If there exist any poles and any zeros, then we have to connect all these poles and zeros with a straight line. Or I may use some other color to understand better. So this is the connections with the other poles. So there is no other poles or zeros. So we have connected these poles with this. We have connected these poles with this, right? So this pole and this pole connections gives you this angle, and this angle is to measure in anti-clockwise directions, right? And here also you see, you just make a horizontal line passing through this pole and make an angle. This is 90 degree. Okay, so what are the different angles you see? You see, this will be 135 degree and this will be 90 degree. So total angle contributed by other poles. Total angle contributed. We have to next step measure the total angle contribution by the poles. Next, total angle contributions by poles, other poles. That is 135 degree plus 90 degree. That means 225 degree. Okay. So 225 degrees is the total angle contribution due to the poles. Similarly, next step we have to find out the total angle contribution due to zeros. So I will just remove it. So total angle contribution. So total next step angle contribution due to zeros. That means if there are any zeros there and there, maybe there is a zero, maybe if there was a zero, say for example, then what you have to do? You have to connect this pole with this zero, because this is your pole under consideration. So you have measured this angle, that is denoted by, this is phi p, this is phi z. So phi z means, for example, this is 45 degree. If maybe there is a zero, so you have to connect this pole with that zero and you have to get the angle, right? So here actually there is no 0. So the total angle contribution due to 0 is 0. Clear? So if there is any 0, you have to connect with this pole at 0 and get the angle. That angle is phi z. So here there is no 0, so angle is 0. So phi z is 0, right? Now this total angle of departure is based on these two values, and we will see how to calculate the angle of departure from the given result. The angle of departure phi d equal to 180 degree minus phi p minus phi z. Okay, so 180 degree minus phi p minus phi z. So this phi p is this 225 here. So this is 180 degree minus 225 degree. This is minus 45 degree. So angle of departure here in this case for this pole is minus 45 degree. The angle is minus. That means you have to measure the angle in clockwise directions. In clockwise direction. That means clockwise directions measurement, how it is done? That means at any point you can put the protector like in the downward directions and you just measure this angle from this root. This will give you the negative angle. This is the concept of drawing the negative angle, right? So we have obtained almost we have come to close our solutions. So now I will just terminate this with a phase diagram, right? With here you see this we have already calculated. This is pole at complex pole, real pole. The real pole terminates an infinity with k is equal to infinity along the asymptote 180 degree line, two asymptote 60 degree and 300 degree left, and you see angle of departure already calculated, that is minus 45 degree. So angle of departure calculation during this we have joined this and this. So next step, what you have to do, you have to draw this angle of departure minus 45 degree. So just make a horizontal line through this pole. Okay, put here one protector and draw the angle clockwise. So if you draw the angle clockwise, this will give you negative value. So this will give you the positive 45 degree angle, and through this point you draw a single line. So this means this actually from this pole a branch will originate, and similarly to this symmetrical you have to draw. This is your positive 45 degree angle, right? If this is contributing angle of minus 45 degree, this is definitely contributing angle of plus 45 degree. So this is the path. That means this root will originate along these directions, move along this asymptote, and finally goes through this j root 2 point to infinity, where the value of k is equal to infinity, right? And similar to that, this point, and not only this angle criteria, automatically there will be symmetric. The root locus branches are symmetrical about the real axis. Okay, so this branch will originate from here, and there is a bend according to requirement, and this goes through j root 2 point and pass to infinity with k is equal to infinity, and this arrow is must. That means this arrow means this is branch is leaving this open loop pole at complex domain with angle of departure. So angle of departure is calculations is done here, and according to that this pole terminates along these directions, this pole is terminating along these directions, this pole is terminating along these directions. And from this concept of Root Locus plot, what we have learned, see, starting from k is equal to 0, here also the value of k is equal to 0, here k is equal to 12, and here k is equal to infinity. That means 0 to 12. That means if the value you see less than 12, greater than 0, system is stable, because all the poles which are lying on the left hand side of the spline, see concept, all the poles starting from here, the path through which it is moving up to these positions, all the poles are lying on the left hand side of the spline. That means if you vary the gain 0 to less than 12, the system is stable. Once the value of k is equal to 12, this just reaches on the imaginary axis. That means this is just going to be unstable, not stable. Initially the amplitude is like this, bounded. Next, what happens once you increase this gain, what happens, you see there will be oscillatory nature. It's actually starting to get unstable. Next, when the value of k is greater than 12, what happens, you see this amplitude is getting increased. That means the system is unstable. So this is your stable region, this is your marginal stable, this is your unstable, and you can see the limit of gain. So once you vary the gain from 0 to infinity, the root locus branches are like this. So certain rules are common, certain points you have to remember, and for complex poles you have to find out the angle of departure in other way. And if required breakaway point is required in some cases, you have to find out the breakaway point, and the common sense you have to apply. Okay, in the next class we will discuss some more problems and different kinds of problems also. Thank you.